Hi, welcome back to College Algebra. This is week 13, which is actually the last week of the semester. We're going to talk about the quadratic formula and graphs of quadratic functions. We'll cover 7.2, 7.4, and 7.5 this week. And here's the list of measurable outcomes. Okay, the quadratic formula. In the last lecture, we had talked about how to solve a quadratic equation by completing the square. We saw that was kind of a tedious process, and so we'd like to kind of avoid doing it for every single problem. And so the quadratic formula is actually, again, we won't go into detail of how this works, but it turns out that the quadratic formula is derived because of completing the square. In other words, what we learned last time, the process of completing the square is used to get the answer to the quadratic equation. And so in other words, it's basically the very last step of completing the square. And so instead of completing the square every problem, we're going to use the formula, which is the last step of it, and just get the solution right away. So this says that if you have ax squared plus bx plus c is 0, and where a is not 0, so that this is quadratic, then the solution to this equation, there's two solutions, and they are minus b plus or minus square root of b squared minus 4ac divided by 2a. And this quadratic formula is very useful because it solves this equation regardless of whether this is factorable or not. In fact, if this is factorable, it's probably the easiest way to do is to factor. But even if this is not factorable, we can use this formula to get the solution without knowing how to factor it. So here it is. Here's an example. Here's the quadratic equation. Again, as always, we always bring everything on the left on one side, so that we try and solve for 0. That's the easiest problem to solve, is to solve for 0 because of the 0 property. So again, notice that we can't factor this. You can try to factor it, but you can't factor this easily. And so, by the way, the quadratic formula, as I said, I think already, but this works for both the case where you can factor or in the case where you cannot factor. If you cannot factor, this would be very helpful. But even if you didn't know how to factor, you can, and it can be factored. This formula still works regardless. Okay, so here's now we know that we have to put everything on one side because we need this to be 0. So now we know what a, b, and c are. So a is 2, for example, b is -3, and c is -5. So now I can plug these values into the quadratic formula. So notice this is minus b. So if b is -3, minus b is positive 3. Negative and -3 is positive 3. And then plus or minus b squared. This is -3 squared minus 4 times a, which is 2, times c, which is -5. So now we have to simplify this radical. This is why we spend so much time on all those radicals, because we're going to need that for this. Notice the inside here, I simplify it into 9 plus 40. And now you get the 49, which is actually a very nice number. So square root of 49, it's just 7. So it's 3 plus or minus 7 divided by 4. So there's two cases, either 3 plus 7 divided by 4 or 3 minus 7 divided by 4. And I get either 5 halves or -1. So that means that this equation has two solutions, 5 halves and -1. It turns out that actually I was wrong earlier. It turns out you can actually factor this into to two terms because these solutions are rational. But if you didn't see how to factor this, notice that the quadratic formula still works, and it gives you kind of a straightforward way of solving a quadratic equation. Let's do an application where you have a rocket that's launched upward from a side of a 144 feet cliff. And suppose that the initial velocity is 112 feet per second. So it turns out that those conditions give us this function for the height of the rocket. And so this function is this quadratic function, where h is the height measured in feet and t is the time after the launch in seconds. So the question here is find the time that the rocket is 208 feet above the ground. So that means that we want to know when the height is 208. So we try and solve this equation. We try and figure out when the height is 208. We try and figure out what time gives us 208. In other words, what's the value of t so that this height function gives you 208. So this is quadratic. I bring everything on one side to solve for 0. I noticed that 16 divides into all these evenly, so divide everything by 16 to make it simpler. This is now a much simpler equation. But notice I can't factor this. I can try, but I can't factor, so I'm going to use a quadratic formula. Apply the quadratic formula, and when I simplify it, I get this. 7 plus or minus root of 33 divided by 2. So either 7 plus root of 33 divided by 2, or 7 minus root of 33 divided by 2. I notice that this division by 2 is everything is divided by 2. This part right here, everything is divided by that bottom. So I can simplify this into these two decimal if I have a calculator, but if not, these are the two solutions to my equation. So that means that the time is either 6.37 seconds or 0.63 seconds, which means that the rocket on the way up, when t is less than a second, it hits the height of 208, and on the way down, after 6.37 seconds later, the rocket comes down, also hitting the height of 208. Okay, and then the radicand that is inside the quadratic formula, the expression b squared minus 4ac is known as the discriminant. So again, let's go back to this. The discriminant is the term that is inside of the radical. B squared minus 4ac, that's called the discriminant. And the discriminant can actually help us figure out how many solutions we get from a radical, from a quadratic equation. And here's so again, b squared minus 4ac is the discriminant. If that discriminant is bigger than 0, then we're going to have two real solutions. And then in that case, if the discriminant is a perfect square, then the solution would be rational numbers. That'd be very nice rational. But if the b squared minus 4ac is not a perfect square, and we have the radical doesn't go away, in other words, then the solution would be irrational numbers because of the radical. And then if the discriminant is less than 0, there are two imaginary solutions. Again, we don't cover this in the class. And then finally, if the discriminant is equal to 0, we have one rational solution. So let's see some examples. So again, this is where we want to figure out the type and the number of solution of an equation without solving for it. So for example, in part A, if I compute the discriminant b squared minus 4ac, plug in all the terms, I get negative 47. Because this is negative, that means that this equation has no real solution. It has two imaginary solutions, but there's no real solutions. And notice here, in this case, we have to bring everything on one side so that you set it equal to 0. Then we know what a, b, and c are. That's a very important step. Now applying b squared minus 4ac. 25. Positive means that this equation has two real solutions. And in fact, 25 is a perfect square. So this equation has two rational solutions, which is nice. That means it's either an integer or a fraction of integers, which are nice solutions. So no radicals for this equation. For this one, you have to do some algebra first, but distributing and then moving everything one side, I can apply the discriminant again. B squared minus 4ac. This is 52. Notice this number is positive, so I do have two solutions. But because this is not a perfect square, my solution will be irrational solutions. And then lastly, this one again, move everything on one side, apply the discriminant, I get 0. So that says that this equation has exactly one solution, and it's one rational solution. So again, we're not solving, we haven't solved these equations, but we at least know how many and what kind of solution we get. So here's a picture of, so you get two solutions if your parabola, the shape of your quadratic function, touches the x-axis twice. See how it touches the axis here twice? That means that the function has two solutions, two zeros, two places where the function is 0. For example, in this case, axis 1, axis 3 will make the function be 0. So these are my two solutions. If my parabola is above the x-axis, then this parabola is never 0. So that equation has no real solution. So this is the two imaginary solution case. And finally, you have the case where you have one real solution. Is where your vertex, or where your quadratic, your parabola touches the x-axis exactly once. So notice two places, no places, and exactly one place. So those are three cases of that we saw from the discriminant. This discriminant is positive in this case because we have two solutions. The discriminant is negative in this case because we have no solution. and then discriminant is 0, is when we have one solution, and exactly one solution. Okay, so here's a function which is a quadratic function. It has that parabola shape. So we want to talk about how to find the discriminant and how to find the x-intercepts as well as the y-intercepts. So A is 1, B is -3, and C is 1. So the discriminant is positive. So we have 2 x-intercepts, right? It's just the case we saw earlier. This case right here, because if the discriminant is positive, we have 2 x-intercepts. So now we know that we have 2. We can solve for them. So again, setting the function be equal to 0. So notice here's the original function. If I want to solve for x-intercepts, I have to set the function being 0. And notice now I can't factor this, so I apply the quadratic formula, and I get and we saw that the discriminant was 5, so we have 2 solutions here. Because this is not a perfect square, my solutions are irrational numbers. So that means that it goes forever without any pattern. This is just an approximation, but so these are the 2 solutions. Notice there's a plus and a minus solution. So those are the x-intercepts. These two x value is where the y value is 0. These are the places where it crosses the x-axis. To find the y-intercept, actually, let's look at the problem again. The y-intercept is always easier to find than the x-intercept. To find the x-intercept, you have to solve for the function being 0, and that might involve some factoring or some quadratic formula. But to find the y-intercept, all you have to do is plug in 0. If I plug in 0, I get 1, so the y-intercept is at 0, 1. Remember, the y-intercept is where the function crosses the y-axis. So here's the y-intercept. Plug in 0 to get 1, give you the y-intercept. But the 2 zeros, the 2 x-intercepts, was harder. We saw that we solved for those by using the quadratic formula to solve when the function is equal to 0. And so we found those 2 zeros. Those are irrational zeros. Okay, so here's kind of a recap of what we talked about. If I want to solve a quadratic equation, there's 2 ways of doing it. There's 3 ways of doing it. One way, the easiest way, is that if the term is easy to factor, that's the best way to do it. Just factor it and solve for 0. And then if you can't factor it, you can complete the square as we saw in the last lecture. But we saw that that process was tricky for some of the problems. But it will be good to do that when you have the case where, in fact, the problem is very easy if you don't have a middle term. So if the middle term is 0, if b is 0 and you have no middle term, then I can just use the square root property. For example, move the c over, divide by a, take the square root both sides. Or if b is even, you can also use the completing the square to do that as well, because you have to remember you have to do the b divided by 2 square the result. But really, I think that for the most part you don't have to do this unless you're asked to, because in this lecture we saw that the quadratic formula works in all cases. It's actually very easy to apply, and so what I recommend is that whenever you have a problem, if it's factorable, that's the best way to do it. But if it's not factorable, I think it's easier to use the quadratic formula, because the quadratic formula is the result of completing the square. It's just the end result. So instead of doing all the steps, the quadratic formula actually gives us the answer right away. And this works for all cases, whether it's factorable or not. The last method here always works. Okay, I want to solve this quadratic. Notice I have to do some algebra first. So foiling this out, combining like terms, so that we get into this format. Notice that we want the one side to be 0. So this equation is factorable, so we should factor it. We don't want to use the quadratic formula. Quadratic formula is still complicated. So if something is factorable, it's easier to factor it. So I'll factor this, and then now either this is 0 where x is 1/2, or this is 0 where x is 1. And so those are the 2 answers I have. And this one is, you notice there's no middle term, there's no p term, the linear term. So this one is easier to just isolate the p square term. So move the 11 over, divide by 9, take the square root of both sides, and then that's it. That's the answer. So this is the easiest case. And then you might have to, you can, when you square root a fraction, we saw that we can apply the square root property by square root at the top and then square root in the bottom to get that simplified form. Okay, finally, the last lecture here, the last section is on graphing quadratic functions. We saw a little bit of this in a couple lectures ago, I believe. But a quadratic function of this form has a form of a parabola, as we saw a couple examples ago. So now we're going to talk about how to actually graph this parabola. We know its basic shape is kind of like a U shape, either facing up or facing down. But the point here is that if A is positive, it's going to open upwards, like this case. If A is negative, it's going to open downward, like this. And then if it opens up, the lowest point is called the vertex. This is the vertex here. And if it opens down, the highest point is also called the vertex. I notice that this parabola is symmetric around. This is some symmetry here. If I cut it down right in the middle here, and I reflect it over that line, this is symmetric around that line called the Axis of Symmetry. It's just that vertical line that cuts right in the middle. Okay, so let's talk about how to graph quadratic function by going through a series of functions that are simple and then combining them in some ways. And so for the easiest case is to look at x squared plus k. So we already saw in one of the last lecture that when you graph x squared, it's just a U shape that goes to the origin. And so this first example is just taking that x squared and then moving up and down. So if k is positive, you move it up. If k is negative, you move it down. So let's see an example. So again, we know that what this looks like, x squared is just the black function here. And g of x is x squared plus 1. So that means I'm taking f and I'm adding 1. So that means I take the black function and move up by 1. Adding a constant, move the entire function vertically in the vertical direction. If I subtract 2, then I just move it down by 2. So that's the blue function. So again, this is something called the parent function, the original function, and then the other two function comes from it. So adding a constant and subtracting, we move it up and down. Okay, the second part is that this one, x minus h squared. So this is going to move left or right by h. And so let's kind of see how that works. So notice here, notice before the plus or minus is done outside of the square, right? You square and then you plus 1, you square and then you minus 2. But notice in this case, you subtract first, then you square. So the order is a little bit different here. So x minus 7 square, x plus 1.6 square. So that means that I take the original function, which is x squared, and I move it right by 7. If it's minus 7, I go to the right side, it's opposite. So now it's the x squared normally is like this. I move to the right by 7. And the other case is where you have, if this is a plus, then I'm actually moving left by 1.6. So I'm taking the function and move left by 1.6. Then another example is that if you multiply x squared by a, then I'm scaling it vertically. Either it's a vertical shrink or vertical stretch. If a is between 0 and 1 and it's positive, then it's a vertical shrink, because if a is less than 1, then I'm shrinking it. If a is bigger than 1, then I'm stretching it by a factor of a. And then if a is positive, right, notice we know that the parabola opens upwards. But if a is negative, the parabola is going to open downward, and then we have to take the absolute value of a. And then the same process, if the absolute value of a is between 0 and 1, I'm shrinking it. If the absolute value of a is bigger than 1, I'm stretching it. So let's see some example. So notice now that I'm multiplying each of the x squared term. This is the original x squared function. I multiply by 2, or I multiply by 1/2. And so here's the pictures. The original function is the black function. The g function multiplied by 2. Again, 2 is bigger than 1. So notice this is positive 2. So because 2 is bigger than 1, I'm going to stretch it vertically by a factor of 2. So whatever it was before is stretched vertically by a factor of 2. On the other hand, if it's 1/2, then we're basically shrinking by a factor of 2. Again, we're dividing by 2 in this case. And so a tells you whether you're stretching or shrinking. And now if a is negative, it's just the opposite direction, right? Negative 1, negative 3, negative 1/3. So the original function is if I negate x squared and I get negative x squared, then I get that the parabola now opens downward but still goes to the origin. Now if I multiply by negative 3, then that means that I'm stretching it vertically but in the other direction by a factor of 3. And then if this is a negative 1/3, then I'm shrinking it by a factor of 3. So notice if I'm stretching it by a factor of 3, then I'm actually making the parabola kind of skinnier. But if I am shrinking it by a factor, if I shrink it, then I make it wider. So maybe I see this one. So again, if I'm stretching it vertically, I make it skinnier because it's going to grow faster. But if I'm shrinking it by a factor, the parabola is wider, so it's going to grow slower than the other ones. Now we combine all of those three operations to one. So remember we saw, let's see the three operations again. The first operation was adding k outside of the x square, which is move up and down. Subtracting h inside the square, move left or right. And then multiplying by a constant, scale it either vertically by a factor or either shrinking or stretching. And so if I combine all those three operations, then I get the k move up and down, the h move left and right, the a will be vertical, stretching, or shrinking. And if I write in this form, this is also known as vertex form. And if it is written in this form, it turns out the vertex of the function is spotted very easily. It's just the h and the k. And notice this is a minus h. And then the axis of symmetry is just the line x is h because it goes to the vertex. Again, if a is positive, it opens upward, and k is the minimum value. K is the y value of the vertex, the minimum. If a is negative, it opens downward, and k is the maximum value. So again, here's a picture. The vertex hk is straight from the vertex form here. And then a is positive means it opens up. If a is negative, it opens down. This is the smallest point. This is the biggest point. Okay, let's do this example. So suppose you have this quadratic function. Notice this is written in vertex form. This is a, this is h, this is k. So let's find the vertex. The vertex is simply 3, 4. Again, this has to be a minus. H is the 3. So 3, 4 is the vertex. And notice that because of what we learned earlier, this is going to move right by 3. Well, okay, we do. There's a couple ways of saying this, but yeah, we move right by 3, up by 4, and then we also stretch vertically by a factor of 2. So maybe it's easy to say stretch out by a factor of 2. Take the original x square, stretch out by a factor of 2 vertically, move right by 3, and then move up by 4. So if I do that carefully, I can actually graph it. The axis of symmetry is very simple. It's just x is equal to 3, which is the h term. And then because a is positive, it's going to open upwards. And so here's the graph. Again, we can find the vertex h comma k. That's 3, 4. The axis of symmetry is the vertical line. X is 3. Notice x is 3 is a vertical line. And then the parabola opens upwards. So if I want to graph this accurately, I can plot the vertex, and then I can maybe pick a point, any point on here, and find out the vertical height. And then that way I can plot it. And I know that the axis of symmetry can help me because it's going to be symmetric around that axis. So the domain of this quadratic function is all real numbers, but notice the range is from 4 to infinity because the range is only all the y values that is 4 or bigger. So the range is from 4 to infinity, including 4. Okay, so here's the recap. The vertex formula. If I have a quadratic function, the vertex formula is found by doing this. Actually, this is not a recap, but this is just a result that we want to remember. To find the I guess here's how you think about this. This is called vertex form because everything's written in this form, and vertex form is the easiest form to work with because it tells us right away what h and k are. H and k is the vertex, so you can spot it right away. So if it's in this form, h and k is given. But if I have a function, a quadratic function in this form, ax squared plus bx plus c, this is sometimes called the standard form. And in this form, it's not so easy to see what the vertex is, so you have to compute it, and the vertex is computed by doing this trick. This is something you want to memorize. It actually comes up a lot. The x value of the vertex is minus b over 2a. Minus b over 2a. And then the y value of the vertex is simply taking that x, plug it into the function. So this is a shortcut to figure out the vertex if the function is given in this form. So for example here, right, I can't see, it's not in the other form, so I can't spot the vertex easily. So I can apply the formula for the vertex by doing minus b over 2a. So for example, minus b over 2a is minus 12 over 2 times negative 2, which is positive 3. So that's the x value of the vertex, which is 3. I take that 3, I plug into the function, and I get 2. So that means that the vertex is at the point 3, 2. The axis of symmetry is x is equal to 3, which is this term right here. X is equal to 3, a vertical line going to this point. Because a is negative, it's going to open downward, and the y. By the way, we don't. I guess if you want, you can also compute the y-intercept, which is very easy to compute. F of 0, plug in 0, you get negative 16. So that's the y-intercept. So having all this information, now we can graph the function. Oh, actually, we have to do one more thing. We have to find the we found the y-intercept. We have to also find the x-intercepts, the zeros. So to do that, we just set the function equal 0. So again, this is where we use the quadratic formula. Set everything to 0. I can factor out negative 2. That will help. And it turns out that this is actually factorable, so I can factor it, and I get two solutions: either x is 4 or x is 2. So those are x-intercepts. So now, after all that work, notice we did a lot of work here. We know we found the vertex, we find the axis of symmetry, we find the y-intercept, we find the x-intercept using either factoring or by quadratic formula. If you can't factor this, you can use the quadratic formula. But having done all that work, now we can graph it. Here's the vertex 3, 2. Here's the axis of symmetry, this pink line. It opens downwards. Here's the y-intercept, which is at negative 16. Here are the zeros, 2 and then 4. Notice that if I have those points, I can connect the dots and get a pretty decent picture of my parabola. So that's how you graph a quadratic function. Here's another one. Same thing. I'm going to apply the ABC to the x-coordinate of the vertex is minus b over 2a. I get that x is 1. Plug in 1 into the function to get 4. So the vertex is 1, 4. To find the y-intercept is very easy. Plug in 0, you get 5. To find the x-intercept, you solve for 0. So this one you can't factor, so you have to apply the quadratic formula. And when you apply it and you try to simplify, you notice that this is a negative 16. So the discriminant is negative. So that means this this function has no real solutions or no x-intercepts. And so if I plot it, I notice that the minimum is above the x-axis, 1, 4, the vertex. It opens upwards. Notice that this function has no x-intercepts. It doesn't cross the x-axis. And we saw that because the discriminant was negative. Okay, great. Thank you for watching.